Hello everyone, myself Dr. M. Pavan Kumar Reddy, Assistant Professor, Department of Mathematics, VNR VJEC. Today our topic, change of variables in triple integrals. So we study change of variables from Cartesian coordinate system to cylindrical polar coordinate system, Cartesian coordinate system to spherical polar coordinate system. Okay, so first we'll see Cartesian to cylindrical polar coordinates. What is the transformation we use? Okay, and what is the equivalent integral? See, for triple integral in Cartesian coordinates with variables x, y, z, the change of variables to cylindrical polar coordinates are r, theta and z. R, theta and z. So, r, theta, z is, see here, if you consider three axes, let's see, this is x-axis, this is y-axis and this is z-axis. Okay, imagine a point in space. Okay, imagine a point in space, say P, it is with coordinates x, y, z in Cartesian coordinates. Okay, now let's draw a line from the pole, this is. Consider its projection in xy plane. So its projection in xy plane is, so this is somewhere here. It is the projection. Let us denote it with say Q. Okay. Now, see the projection. Now, this is. So now the projection, and let's join OQ. See, the angle made by the projection of this line, okay, OP, with the positive direction of x-axis is theta. R is the distance of that point from the pole and Z is height from the xy plane, height of that point from the xy plane. So what this is the meaning of R, theta and Z. Okay, and what is the transformation we use here is x is equals to r cos theta, y is equals to r sin theta and z is equals to z itself. And now, while transforming from one coordinate system to another coordinate system, we use Jacobian. Okay, so let's determine first Jacobian of x, y, z with respect to r, theta, z. Okay, that is dou of x, y, z by dou of r, theta, z. So Jacobian in three variables is, it leads to a 3 by 3 matrix determinant. That is, first row are the elements of partial derivatives of x with respect to r, theta and z. Second row are the partial derivatives of y with respect to r, theta, z. Third row are the partial derivatives of z with respect to r, theta and z. Let's determine the partial derivatives. Dou x by dou r. See, x derivative with respect to r, so we treat theta as constant. So cos theta constant, r derivative with respect to r is 1. So it is cos theta. And x derivative with respect to theta, r is constant. Cos theta derivative minus sin theta. And r cos theta derivative with respect to z. There is no contribution of z. R and theta both are constants. So 0. Similarly, dou y by dou r. Y derivative with respect to r sin theta. With respect to theta, r constant cos theta. With respect to z, there is no contribution, it is 0. And next, z derivative with respect to r, theta, z. R, there is no contribution of r and theta. So r with respect to r 0, with respect to theta 0. And then with respect to z is 1. Now this is a 3 by 3 matrix determinant. So if you evaluate this determinant, I'm not going to the details. So if you evaluate the determinant, we get r into cos square theta plus sin square theta. This is 1 into, say, the minor, 1 into minor of this. So remove this row and column. So cos theta into r cos theta, r cos square theta minus sin theta into minus r sin theta is minus of minus plus r sin square theta. R common, cos square theta plus sin square theta 1. So the Jacobian is r. Okay, now the equivalent integral is, actually what is the volume in Cartesian coordinates? What is the integral in Cartesian coordinates? Triple integral over V f of x, y, z dx, dy, dz. The equivalent integral in cylindrical polar coordinates is, since x equals to r cos theta, we substitute, y equals to r sin theta, we substitute, and z is equals to z into Jacobian dr d theta dz. We got Jacobian is equals to r. See, after substituting x, y, z, so now the integrand is completely becomes the function of r, theta and z. So therefore it is triple integral over the volume, the equivalent volume in cylindrical polar coordinates. That's why I am denoting this region. See, in Cartesian coordinates, the volume I am denoting with V. In cylindrical polar coordinates, it is V star. So V star, capital F of r, theta, z, r into dr into d theta, dz. Okay, so this is the equivalent integral in cylindrical polar coordinates. See, now we'll see spherical polar coordinates, Cartesian to spherical polar coordinates. Spherical polar coordinates means in the similar manner we consider the x, y, z axis in three-dimensional space. Let us consider these three dimensions, x, y and z. Okay, let's consider a point in space. It is P with coordinates x, y and z. So consider its projection. Consider its projection in xy plane and see here join OP and OQ. Let us denote it with Q. Okay. Now what is R? R is the distance of the point from the pole origin. Also we call in Cartesian system OQ. And this OP makes an angle theta with the z-axis. And what is pi is? Pi is the angle made by this projection of OP, that is OQ, with the positive direction of x-axis. This is pi. These are the coordinates r, theta and pi. Now, what is the transformation we use while transforming from Cartesian coordinate system to spherical polar coordinate system? That is, x is equals to r sin theta cos pi, y is equals to r sin theta sin pi, and z is equals to r cos theta. As usual, we determine the Jacobian of these x, y, z with respect to r, theta, pi. Okay, that is partial. See, this is the another way of representation of the partial derivative. X suffix r. Remember, x suffix r is nothing but dou x by dou r. Dou x by dou r. In the similar manner, other partial derivatives. See, the 3 by 3 matrix Jacobian of x, y, z with respect to r, theta, pi means first row are the elements of the partial derivatives of x with respect to r, theta and pi, with x with respect to r, theta, pi. Second row y with respect to r, theta, pi. Third row z with respect to r, theta, pi. Let's determine the partial derivatives. X with respect to r, so we treat theta pi constant, sin theta cos pi, r derivative 1. And y, x derivative with respect to theta, we treat r pi constant, sin theta derivative cos theta, r cos theta cos pi. Next, cos pi derivative, it is minus sin pi. That's why minus r sin theta sin pi. Similarly, y derivative with respect to r theta pi, with respect to r, it is 1. 1 into sin theta sin pi. With respect to theta, r cos theta sin pi. With respect to pi, it is r sin theta cos pi. Next, z derivative with respect to r theta pi. Z derivative with respect to r, it is cos theta. With respect to theta, cos theta derivative minus sin theta. So minus r sin theta. There is no contribution of pi. So z derivative with respect to pi is 0. Okay. So if you evaluate the 3 by 3 matrix determinant, you are going to get the Jacobian as r square into sin theta. R square into sin theta. Okay. Now let's see problems. Now let's substitute this, that the integral in Cartesian coordinates which will be equivalent to the corresponding integral in spherical polar coordinates is, this is the integral in Cartesian coordinates, triple integral over V, f of x, y, z, dx, dy, dz. The equivalent, the volume in the spherical polar coordinates is, let's denote it with V star. Substitute x, y, z equals to r sin theta cos pi, r sin theta sin pi, r cos theta respectively. And Jacobian dr d theta d pi, and if you substitute r this transformation, this integrand is a function of now r theta pi. Let's denote with capital F, and Jacobian is r square sin theta dr d theta and d pi. Dr d theta and d pi. Let's see a problem. See, evaluate triple integral z into x square plus y square into dx, dy, dz over the volume of the cylinder x square plus y square equals to 1, bounded between z equals to 2 and z equals to 3 by cylindrical polar coordinates. See, it is x square plus y square equals to 1, looks like a circle. But this type of circle is lying between the planes z equals to 2 and z equals to 3. That is, if you consider this is x-axis and this is y-axis, x square plus y square equals to 1, which represents a circle. Okay. Now, this z equals to 2 and z equals to 3. So, means such type of circles are located as z as the axis of the cylinder. Now, x square plus y square equals to 1 circle between z equals to 2 and z equals to 3. Z equals to 2 is a plane which is parallel to xy plane. Z equals to 3 is a parallel plane which is parallel to xy. So that circles which kept between z equals to 2 and z equals to 3 form a cylinder. Okay. Now let's identify the limits and we evaluate by transforming it into cylindrical polar coordinates. So we are asked to evaluate this integral by transforming it into cylindrical polar coordinates. So what are the cylindrical polar coordinates we have? So we have x is equals to r cos theta, y is equals to r sin theta, z is equals to z, and of course what is dx dy dz? Dx dy dz is equals to Jacobian into dr d theta dz. What is Jacobian? R dr d theta and dz. Our objective here is to identify the corresponding limits for r, theta and z. Now what are the limits for r now here? R is actually the radius. So therefore, it's the distance of the point on the cylinder from the pole. So point on the cylinder, and this is the radius, of course, r. What is the radius of the circle, the cylinder? Which is 1. 1 square is 1. So therefore, r varies from 0 to 1. Of course, theta. What is theta now? Theta varies from 0 to 2 pi, which is a circle. Okay, 360 degrees. 0 to 2 pi. And z is height of the cylinder, which varies from, it is given, the cylinder is placed between z equals to 2 and z equals to 3. So z varies from 2 to 3. Okay. Now, therefore, of course, now let's convert the integrand also into corresponding cylindrical polar coordinates. So now what is z into x square plus y square? So what is z here? Z is equals to z only. Since z equals z only, transformation. What is x? X is equals to r square cos square theta plus y equals to r square sin square theta, which is equals to z into r square common. Okay, cos square theta plus sin square theta is 1. So that means it is, the integrand is now, it is r square into z. So therefore, triple integral, it is z into x square plus y square into dx dy into dz equals to, the equivalent integral in cylindrical polar coordinate is, it is z varies from 2 to 3 and theta varies from 0 to 2 pi and r varies from 0 to 1, and the integrand is, it is z into r square into, what is dx dy dz? It is r into dr into d theta into and dz. Okay. Now let's evaluate the integral. Z into r cube. Let's write. So therefore, evaluating the integral, z varies from 2 to 3 and theta varies from 0 to 2 pi and r varies from 0 to 1. Integrand is zr cube now. It is z into r cube dr d theta and dz. Observe here, z limits are constants, theta limits are constants, r limits are also constant. So therefore, the order of integration here is immaterial. So the order you can do first r theta z, first r then theta then z, r first z first then theta then r first theta then r then z. Either way you can do. Okay, anyway, we'll follow this order as it is. Z varies from 0 to 2 to 3, theta varies from 0 to 2 pi, and r z constant integrating with respect to r cube integral is r to the power of 4 by 4. Upper limit is 1, lower limit is 0. It is d theta into dz. Let's substitute the limits. It is z varies from 0 2 to 3 and theta varies from 0 to 2 pi, and next z into r. Instead of r we substitute 1 by 4 minus substitution of lower limit 0, no contribution. So d theta into dz, that is equals to, let's write this 1 by 4 outside of the integral. Next z varies from 2 to 3 and theta varies from. So therefore let's integrating this with respect to theta now. Integrating with respect to theta. So integral 1 into d theta is theta. So therefore theta, of course there is z, keep it as constant. Upper limit is 2 pi, lower limit is 0 into dz. So therefore, which is equals to, it is 1 by 4 integral z varies from 2 to 3. It is z into, instead of theta we substitute upper limit 2 pi, lower limit is 0, no contribution, into dz. That is equals to, this 2 pi is constant which can be written outside. So it is 2 pi divided by 4. Now it becomes integral z into dz. Integral z dz is z square by 2. Upper limit is 3 and lower limit is 2. Therefore it is pi by 2, 2 to the 4. So pi by 2 into 3 square, it is 9 by 2, minus instead of z 2 square, it is 4 by 2. That is equals to pi by 2 into 9 minus 4, it is 5 by 2. That is equals to, it is 5 pi by 4. So this is the value of the integral by applying cylindrical polar coordinates to the given integral. Okay, by transforming this integral into cylindrical polar coordinates and we evaluated, we obtained 5 pi by 4. Okay, I hope you understand. Now we'll see one more problem. We evaluate this by changing it into spherical polar coordinates. So change to spherical polar coordinates and hence evaluate this integral. See, in spherical polar coordinates, what are the limits here is, it is r varies from 0 to the radius of the sphere. 0 to radius of the sphere. 0 to radius of the sphere. And next theta which is the angle, is varies from 0 to pi. It is vertical angle. And pi which is varies from 0 to 2 pi. This is horizontal angle. Okay, so these are the limits for r, theta, pi when the region is, volume is bounded by the surface sphere. Okay, now so here change to spherical polar coordinates and hence evaluate this integral where v is the volume of the sphere. So here we have to evaluate this integral, okay, over the sphere. Okay, now over the sphere, the transformation we use here is, let x is equals to r sin theta into cos pi, y is equals to r sin theta into sin pi, z is equals to r cos theta. This is the transformation. Along with this, dx into dy into dz is equals to Jacobian of dr d theta d pi. The Jacobian here is r square into sin theta dr d theta and d pi. Dr d theta and d pi. Okay, now the transformation and dx dy dz. Okay, now let's convert this integrand also in terms of r theta pi. Let's consider what is actually x square plus y square plus z square. Now x square plus y square plus z square equals to, what is x square? R square sin square theta, it is cos square pi, plus y square r square sin square theta into sin square pi plus z equals to r square cos square theta. Let's simplify. This is from the first two terms, let's take r square sin square theta common. Then we have it is cos square pi plus sin square pi. What is cos square pi plus sin square pi? Of course, we know it is 1. Cos square pi plus sin square pi is 1. So therefore, r square sin square theta, this is equals to 1 plus r square cos square theta, this is equals to r square. Common again, it is sin square theta plus cos square theta. Again, cos square theta plus sin square theta 1, that is x square plus y square plus z square equals to r square. Now the integrand is completely function of r theta pi. Now let's substitute in the transformation and evaluate the integral. So that is, what is that integral? Triple integral over the volume V. It is dx dy dz dx dy dz divided by x square plus y square plus z square, which is equivalent to the corresponding. See here, of course, it's a sphere, no? What are the limits? R varies from 0 to radius of the sphere. What is the radius of the sphere? Of course, it is a. And what are the limits for pi? Horizontal angle. So 0 to it is 2 pi. And what are the limits for theta? It is 0 to pi. So these are the limits for r, theta and pi. Now let's substitute here. It is first it is say pi limits. Pi varies from 0 to 2 pi and theta varies from 0 to pi and r varies from 0 to a. Okay, what is x square plus y square plus z square? We got it as r square, no? So therefore, it is 1 by r square. What is dx dy dz? Dx dy dz equals to r square sin theta. It is r square sin theta into dr, d theta and d pi. Of course, this r square gets cancelled. Now, see again here, r, theta, pi limits are all constants. You can integrate in any order. So therefore, first it is, say, pi varies from 0 to 2 pi and theta varies from 0 to pi. Let's integrate with respect to r first. Sin theta is constant. Okay, integral 1 dr is r, upper limit a, lower limit 0, d theta, d pi, which is equals to integral pi varies from 0 to 2 pi and theta varies from 0 to pi. It is sin theta into, instead of r, we have to substitute the limits, no? A and 0, upper limit a, lower limit 0, a minus 0, a. So a is constant. Right, let's write here. It is d theta and d pi. This is a is constant, written out, we can write outside of the integral. Pi varies from 0 to 2 pi. Let's integrate with respect to theta. Sin theta integral is minus cos theta. Upper limit is pi, lower limit is 0. Our upper limit is pi, lower limit is 0. That is equals to a into integral pi varies from 0 to 2 pi. Let's substitute the limit instead of theta, pi minus cos pi. Substitution of lower limit minus into this minus becomes plus. It is cos 0 into d pi. This is equals to a into pi varies from 0 to 2 pi. Of course, we know that what is cos pi value? Cos pi value is minus 1. Minus 1 into minus plus 1. Plus cos 0 plus 1 into d pi. So 1 plus 1 is 2, which can be written outside of the integral. Integral 1 into d pi, which is pi. Upper limit is 2 pi, lower limit is 0. That is 2a. It is substitution of the limits. 2 pi minus 0, it is 2 pi. Therefore, it is 4 pi a. 4 pi a. So this is the value of the integral, which is obtained by changing a given integral into spherical polar coordinates. Okay, I hope you understand. So work out these two problems. So by transforming this integral into cylindrical polar coordinates and evaluate. Okay, and also evaluate this integral by changing it into spherical polar coordinates. Okay, thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.